You are looking at a photograph of something that should not exist. It appears on your screen as a tiny smudge, reddish, compact, unremarkable at first glance. One of thousands of similar points of light scattered across the image like grains of sand on black velvet. But this particular grain of sand has traveled for over 13 billion years to reach you. The light you are seeing was emitted when the universe was less than 300 million years old. And according to everything physicists thought they knew about how reality works, this object should be impossible. It is too big, too bright, too mature, too organized. It breaks the rules, and it is not alone. Hundreds of similar objects have now been catalogued, each one a small rebellion against our most carefully constructed model of the cosmos. Some appear to be galaxies, more massive than they have any right to be. Others seem to be black holes that grew too large too quickly. A few resist classification entirely, combining features that have never been observed together, belonging to no known category of astronomical object. The scientists studying these anomalies have given them evocative names: little red dots, universe breakers, astronomy's platypus. They do not yet know what they are looking at, but they know this: something about our understanding of the universe is wrong. Imagine you have spent your entire life studying a map. Not just any map, but the most detailed, accurate, thoroughly tested map of reality ever created. Generations of the brightest minds humanity has produced have spent a century refining it, checking every measurement, correcting every error, until it matches nearly everything you observe with extraordinary precision. And then one day, you look through a new window and you see mountains where your map shows flat plains, rivers flowing uphill, cities that should not exist for another 1,000 years, already thriving. That is not a metaphor. That is what is happening right now in observatories around the world, as astronomers struggle to make sense of what the James Webb Space Telescope has revealed about our universe. Before we go any further, you need to understand what we thought we knew, because the story of what James Webb has found only makes sense if you first understand what we were absolutely certain we would find. Our map of the universe is called the Lambda-CDM model. Lambda stands for the cosmological constant, a measure of dark energy, and CDM stands for cold, dark matter. This model is not a guess or a theory in the colloquial sense. It is the standard model of cosmology, built on nearly a century of observations, backed by mountains of evidence, refined by thousands of the most rigorous experiments in scientific history. Think about what it means for a scientific model to achieve this status. The Lambda-CDM framework has successfully predicted the cosmic microwave background radiation with extraordinary precision. It explains the large-scale distribution of galaxies across the universe. It accounts for the observed acceleration of cosmic expansion. It matches the abundances of light elements like hydrogen, helium, and lithium that were forged in the first few minutes after the Big Bang. When the Planck satellite mapped the tiny temperature fluctuations in the cosmic microwave background with unprecedented accuracy, the Lambda-CDM model passed every test. This is not a theory that arose from armchair speculation. It emerged from over a century of painstaking observation and theoretical development. From Einstein's general relativity, through Hubble's discovery of cosmic expansion, through the detection of the cosmic microwave background in 1964, through the shocking discovery of dark energy in 1998. Each generation of astronomers has tested it, challenged it, tried to break it. And while the model has been refined and adjusted over the decades, its core predictions have held up again and again. According to this model, our universe began 13.8 billion years ago in a singular event we call the Big Bang. In that first instant, all of space, all of time, all of energy exploded into existence from a point of infinite density. The universe expanded and cooled. Within the first 3 minutes, the lightest elements, hydrogen and helium, formed. For the next 380,000 years, the cosmos was a fog, so hot and dense that light could not travel through it. Then came a moment called recombination. The universe cooled enough that electrons could bind to atomic nuclei for the first time, and suddenly light could move freely through space. That light is still traveling today. We call it the cosmic microwave background, and it represents a snapshot of the universe when it was just an infant, a time before stars, before galaxies, before anything we would recognize. The cosmic microwave background is perhaps the most important piece of evidence in all of cosmology. It was first predicted in the 1940s and detected accidentally in 1964 by Arno Penzias and Robert Wilson, who won the Nobel Prize for the discovery when you tune an old television to a channel with no signal. Some of that static is actually the cosmic microwave background. You are watching the afterglow of creation. After recombination came the cosmic dark ages. For hundreds of millions of years, the universe was filled with nothing but neutral hydrogen gas, cooling, drifting, waiting. There were no stars to light it, no galaxies to structure it, just an endless fog of atoms expanding into the void. This is difficult to visualize. We are so accustomed to a universe filled with points of light, with stars and galaxies and nebulae, that imagining absolute darkness requires a kind of mental effort. But for the first few 100 million years, that was reality. The universe was black. Not the black of space between stars, but the black of nothing at all. No light, no sources of light, just cooling gas in an expanding void. During this period, something crucial was happening beneath the surface. Dark matter, that mysterious substance that makes up about 27% of the universe's energy content, was slowly pulling ordinary matter together through gravity. The tiny fluctuations imprinted in the cosmic microwave background, variations in density of just 1 part in 100,000, were becoming seeds for structure. Where there was slightly more matter, gravity pulled in more matter. Dense regions became denser. The first dark matter halos began to form, and then, somewhere between 100 and 250 million years after the Big Bang, something extraordinary happened. The first stars ignited. These were not stars like our sun. They were monsters in a universe with no heavy elements, no carbon, no oxygen, no iron. The first stars were built from pure hydrogen and helium, and they grew to hundreds, perhaps thousands of times the mass of our sun. They burned hot and fast and died young, exploding as supernovae, seeding the cosmos with the first metals. Astronomers call these hypothetical first stars population 3 stars. They have never been directly observed, though they must have existed. Without them, there would be no carbon in your body, no oxygen in the air you breathe, no iron in your blood. Every atom heavier than lithium in the universe was forged inside a star and spread through space when that star died. The calcium in your bones came from a supernova explosion. The gold in any ring you might wear was created in the collision of neutron stars. You are, quite literally, made of stardust. But the first generation of stardust makers, the population 3 stars, remain elusive. They lived and died so early in cosmic history that their light has been stretched beyond recognition by the expansion of space. Even the most powerful telescopes struggle to see them directly. What we observe instead are their descendants, the second and third generation stars that formed from gas already enriched with the products of earlier stellar deaths. Around these dying giants, the first small galaxies began to form, tiny, chaotic collections of stars, gradually merging with one another, growing larger over billions of years through countless collisions and interactions. This is how we believed all large galaxies came to be, including our own Milky Way. Start small, merge often, grow slowly. This process is called hierarchical structure formation, and it is one of the core predictions of the Lambda-CDM model. In this framework, the universe builds itself from the bottom up. Small things form first and combine to make larger things. Dark matter halos merge, dragging their baryonic contents together. Dwarf galaxies collide and coalesce. Over billions of years, these repeated mergers produce the massive elliptical and spiral galaxies we observe in the local universe. The timescales involved are crucial. Building a galaxy like the Milky Way, with its 400 billion stars arranged in a graceful spiral spanning 100,000 light years, is not something that happens quickly. It requires repeated mergers. It requires time for gas to cool and collapse into stars. It requires generations of stellar life and death to enrich the interstellar medium with heavy elements. According to the standard model, you simply cannot rush this process. Physics sets limits. The Lambda-CDM model predicted that if we could look far enough back in time, if we could see the universe as it was in its first few 100 million years, we would find these primordial galaxies. And they would be tiny, faint, messy. Nothing like the grand spiral and elliptical galaxies we see in the modern universe. Everything we had observed supported this prediction. The Hubble Space Telescope, our previous most powerful eye on the cosmos, saw exactly what we expected. Young galaxies were small and irregular. Older galaxies were larger and more structured. The timeline made sense. The physics worked. The math checked out. Hubble pushed our observations back to about 400 million years after the Big Bang, a cosmic redshift of around 11. At these distances, even Hubble's extraordinary capabilities were stretched to their limits. The telescope could detect galaxies, but barely. The images were fuzzy. The spectroscopic data was noisy. The record-breaking galaxy GNZ 11, discovered by Hubble in 2016 at a redshift of 11.1, was little more than a smudge of light on the edge of detectability. Still, even these limited observations seemed consistent with the standard model. Early galaxies appeared small and faint, as predicted. They showed signs of active star formation, as expected. They seemed to be the building blocks from which larger galaxies would eventually form. We were so confident in this model that we built the James Webb Space Telescope specifically to confirm it. Webb was designed to peer into the epoch of Ryanization, that critical period when the first galaxies flooded the universe with ultraviolet light stripping electrons from hydrogen atoms and ending the dark ages forever. We expected to see the dim glow of the first stellar nurseries. We expected to watch galaxies being born. The telescope's specifications were driven by this goal. Its primary mirror, 6.5 meters in diameter and composed of 18 hexagonal gold-plated beryllium segments, was designed to collect enough light to see the faintest objects in the early universe. Its sun shield, a 5-layer structure the size of a tennis court, was designed to keep the telescope cold enough to detect infrared radiation without interference from its own heat. Its suite of instruments, including cameras and spectrographs operating at wavelengths from 600 nanometers to 28 microns, was designed to analyze the stretched, redshifted light from the cosmic dawn. The development of the James Webb Space Telescope took over 20 years and cost approximately $10 billion. It involved contributions from NASA, the European Space Agency, and the Canadian Space Agency. Thousands of engineers and scientists worked on the project. When it finally launched on an Ariane 5 rocket from French Guiana on Christmas morning, 2021, the collective anxiety of the astronomical community was palpable. So many things could go wrong. A single failed deployment sequence, a single stuck mechanism, could doom the entire mission. But everything worked. The sun shield unfurled perfectly. The mirror segments aligned with nanometer precision. The instruments cooled to their operating temperatures. And when the first images came back, they exceeded all expectations. What we did not expect was what those images actually showed. The James Webb Space Telescope launched on Christmas Day, 2021. It traveled 1 million miles from Earth to a point called the second Lagrange point, where the gravitational influences of the Earth and Sun balance out, allowing the telescope to orbit in relative stability while keeping its enormous sun shield perpetually facing our star. Webb sees primarily in infrared light. This is crucial for studying the early universe because of a phenomenon called redshift. As light travels through expanding space, its wavelength stretches. The farther light has traveled, the more it has stretched, and the redder it appears. Light from the most distant objects in the universe, light that began its journey more than 13 billion years ago, has stretched so far that it has shifted entirely out of the visible spectrum and into the infrared. This is worth pausing to appreciate. When we look at a galaxy with a redshift of 14, we are not seeing that galaxy as it exists today. We are seeing it as it was 13.5 billion years ago, because that is how long its light has been traveling toward us. The farther we look in space, the farther we look back in time. Webb is not just a telescope. It is a time machine. The mathematics of redshift are straightforward, but the implications are profound. At a redshift of 10, the wavelength of light has been stretched by a factor of 11. Ultraviolet light emitted by hot young stars is shifted into the near-infrared. At redshift 14, the stretching factor is 15. Even visible light is pushed well into the infrared. This is why Hubble could only glimpse shadows at the cosmic frontier. Its eyes were tuned to visible and ultraviolet light. Webb was built specifically to see infrared radiation, to peer through the redshift, to witness the universe as it was when it was just a few 100 million years old. The Lagrange 2 point, where Webb orbits, is a remarkable piece of celestial real estate. Located about 1.5 million kilometers from Earth, directly opposite the Sun from our perspective, it offers a thermally stable environment perfect for infrared observations. The telescope's sun shield always faces the Sun, keeping the mirrors and instruments perpetually in shadow, where they cool to temperatures around minus 233 degrees Celsius. At this temperature, the telescope can detect the faint infrared glow of the most distant objects in the universe without being blinded by its own heat radiation. In the summer of 2022, Webb released its first images, and within weeks, astronomers began sending each other confused, excited, alarmed messages. Something was wrong with the map. The first hint came from a research team analyzing data from Webb's Cosmic Evolution Early Release Science Survey, called CEARS. This was one of the telescope's flagship early science programs, designed to provide a statistical sample of galaxies across cosmic time. The survey targeted a patch of sky near the constellation Ursa Major, a region previously studied by Hubble as part of its extended Groth Strip survey. By observing the same area with Webb's vastly superior infrared capabilities, astronomers could directly compare what the two telescopes revealed. They were looking at distant galaxies, measuring their brightness and colors to estimate how far away they were and how massive they might be. The technique is called photometric redshift estimation. By analyzing how much light a galaxy emits at different wavelengths, astronomers can infer how much that light has been stretched by cosmic expansion, and therefore how old and how distant the galaxy is. And what they found made no sense. There were galaxies in the early universe that appeared to contain as many stars as the Milky Way. The Milky Way is a mature galaxy. It took billions of years to accumulate its 400 billion stars. These galaxies appeared to have reached similar sizes when the universe was only 500 to 700 million years old. To understand why this is shocking, consider the timescales involved. In the Lambda-CDM model, a galaxy needs to assemble dark matter into a halo, collect gas into that halo, cool the gas enough for it to collapse, ignite stars, let those stars live and die, recycle the enriched gas into new generations of stars, and repeat this process many times. Each of these steps takes time. The cooling of gas, in particular, cannot happen instantaneously. The physics of radiative cooling sets fundamental limits. For a galaxy to contain 100 billion stars within the first 700 million years of cosmic history would require star formation rates that seemed impossible. The gas would need to convert into stars with nearly perfect efficiency. There would be no time for the slow, steady growth that the standard model predicted. The galaxies would essentially need to skip their adolescence entirely and jump straight to maturity. Joel Lager, an assistant professor of astronomy and astrophysics at Penn State University, was one of the scientists analyzing the data. His team called these objects universe breakers because they seemed to violate everything the standard model predicted should be possible. We had specific expectations for the type of galaxies that live in the early universe, Lager wrote. They are young and small. Previous studies of the early universe with Hubble and other instruments tend to find small, blue baby galaxies at early times, objects which have just recently formed out of the primordial cosmic soup and are themselves building their early stars and structures. Instead, Webb was finding what appeared to be massive, mature, red galaxies. Red color in a galaxy typically indicates old stellar populations, stars that have already burned through their hot, blue phase and settled into cooler, redder states. This was the opposite of what everyone expected. The initial reaction in the astronomical community was measured skepticism. Maybe there were errors in the measurements. Maybe the redshifts were being calculated incorrectly. Maybe what looked like massive galaxies were actually something else entirely. So astronomers did what they always do. They gathered more data. They refined their instruments. They checked and rechecked their math. The universe breakers did not go away. As the months passed, Webb kept staring into the cosmic dawn, and the list of anomalies kept growing. One of the most perplexing discoveries involved a new class of objects that astronomers began calling little red dots. These tiny reddish points of light appeared scattered throughout Webb's deep field images. They were compact, they were surprisingly bright, and they defied classification. The story of the little red dots is worth telling in detail because it illustrates how science actually works when confronted with the unexpected. It is not a story of instant revelation. It is a story of confusion, debate, revision, and gradually improving understanding. When astronomers first began noticing these objects in Webb's early data, they appeared to be point sources, meaning they were too compact for Webb to resolve any internal structure. They showed up as tiny dots, not extended smudges like normal galaxies. Their light was distinctly red, which could indicate either old stellar populations or significant dust absorption or both. The initial assumption, naturally, was that they might be quasars. A quasar is the extremely luminous center of a galaxy powered by a supermassive black hole actively consuming matter. As gas spirals into the black hole, it heats to millions of degrees and emits enormous amounts of radiation. Quasars are so bright that they outshine their entire host galaxies, making them appear point-like even when viewed from billions of light years away. When astronomers first analyzed the little red dots, some thought they might be quasars, the brilliant cores of galaxies powered by supermassive black holes voraciously devouring matter. Quasars are point-like sources because the light from the black hole's accretion disk overwhelms everything around it. But the spectra of the little red dots did not match quasars. They showed narrow emission lines rather than the broad ones typical of quasar activity, suggesting the gas around them was moving too slowly to be near a supermassive black hole. This is a technical but crucial point. In a quasar, gas is orbiting the central black hole at tremendous velocities, sometimes exceeding 10% of the speed of light. When this fast-moving gas emits light, the Doppler effect broadens the emission lines, spreading them across a wide range of wavelengths. The width of these lines directly tells us how fast the gas is moving. But the little red dots showed narrow emission lines. The gas was moving relatively slowly. If these were black hole-powered systems, something was very different from normal quasars. Others thought they might be extremely compact galaxies caught in an intense burst of star formation. But if so, these galaxies were impossibly dense. The light they emitted implied stellar densities that defied known physics. Bingji Wang, a NASA Hubble Fellow at Princeton University, pointed out that if these were purely stellar systems, the night sky of such a galaxy would be dazzlingly bright, packed with stars at concentrations we have never observed anywhere in the universe. Consider what she means. In our own galaxy, the nearest star to the Sun, Proxima Centauri, is over 4 light-years away. At night, we see perhaps a few thousand stars with the naked eye, scattered across the celestial sphere. In the hypothetical galaxy implied by the little red dots, stars would be packed so densely that the night sky would blaze with brilliant light. There would be no true darkness. The energy density would be extraordinary. This seemed physically implausible. Stars cannot form in arbitrarily dense configurations. Gravitational interactions would disrupt such systems. The physics of star formation sets limits. By 2024, over 300 little red dots had been catalogued. 80% of them showed signatures suggesting they might contain active galactic nuclei, which would mean supermassive black holes. But these black holes, if they existed, were also impossible. They were far too massive for such young, small galaxies. In the local universe, there is a well-established relationship between the mass of a galaxy's central black hole and the mass of stars in the galaxy itself. The ratio is typically about 1 to 1,000. In these early galaxies, the ratio appeared to be 1 to 10, or even 1 to 1. The black holes seem to outweigh their own galaxies. This relationship, known as the black hole to stellar mass ratio, is one of the most robust empirical relationships in extragalactic astronomy. It has been measured in hundreds of local galaxies and appears to be remarkably consistent. The fact that early galaxies violate this relationship so dramatically suggests either that our measurements are wrong or that something fundamentally different was happening in the early universe. Something was profoundly wrong. In January 2024, an international team using Webb observed the most distant galaxy ever confirmed, a system called JWST 14-0. The light from this galaxy had been traveling for over 13.5 billion years. When that light was emitted, the universe was only 290 million years old, roughly 2% of its current age. The name itself tells a story. JADES stands for the JWST Advanced Deep Extragalactic Survey, one of the flagship observing programs using the telescope. GS indicates the galaxy is in the Goods South Field, a well-studied patch of sky that has been observed by generations of telescopes. The Z14-0 designation refers to its approximate redshift of 14 and distinguishes it as the primary object among any candidates at that redshift. A redshift of 14 means that the light from this galaxy has been stretched by a factor of 15 as it traveled through expanding space. Ultraviolet light emitted by hot young stars has shifted all the way into the near-infrared, and even optical light has been pushed to wavelengths beyond what any previous telescope could detect. JADES GS-DZ 14-0 should not exist. According to the standard model, a galaxy forming that early should be tiny and faint, a dim smudge of a few million stars struggling to coalesce from the primordial gas. The hierarchical buildup of structure takes time. Dark matter halos need to form first, then grow through mergers. Gas needs to fall into these halos, cool, and fragment. Stars need to form, live, die, and recycle their material into new generations. At 290 million years after the Big Bang, there simply should not have been enough time for all this to happen at the scale Webb observed. Instead, Webb revealed a galaxy spanning over 1,600 light-years, containing several 100 million solar masses worth of stars, shining with a luminosity that implied active, vigorous star formation. To put this in perspective, our own Milky Way galaxy spans about 100,000 light-years. It contains roughly 400 billion stars accumulated over more than 13 billion years. Jade's JWST 14-0, while much smaller, had already assembled a significant fraction of a mature galaxy's stellar mass in less than 300 million years. The star formation rate required to achieve this would be extraordinary, perhaps 30 to 50 solar masses per year, compared to the Milky Way's current rate of about 1 solar mass per year. Stefano Carniani of the Scuola Normale Superiore in Pisa, the lead author on the discovery paper, expressed the shock felt by many in the field. It is stunning that the universe can make such a galaxy in only 300 million years, he said. But it was not just that this galaxy existed, it was what it contained. Follow-up observations detected strong emission lines from oxygen and hydrogen, indicating that massive stars had already lived and died in this galaxy, spreading their fusion products throughout the interstellar medium. The presence of oxygen was particularly significant. In March 2025, astronomers using the Atacama Large Millimeter Array in Chile confirmed oxygen in Jade's JWST 14-0, the most distant detection of that element ever achieved. The ALMA observations were remarkable in their precision by detecting the fine structure emission line of doubly ionized oxygen at a rest wavelength of 88 microns, shifted by the cosmic expansion to a much longer wavelength. Astronomers could measure the galaxy's redshift with extraordinary accuracy to within 0.05%. This eliminated any remaining uncertainty about the galaxy's distance and age. Oxygen is not a primordial element. It was not created in the Big Bang. Every oxygen atom in the universe was forged inside a star and released when that star died. For oxygen to be present in such quantities, entire generations of massive stars must have already been born, burned through their fuel, and exploded as supernovae. All within the first 290 million years of cosmic history, the process by which oxygen is created, called stellar nucleosynthesis, occurs in the cores of massive stars through a series of nuclear fusion reactions. Hydrogen fuses to helium. Helium fuses to carbon. Carbon fuses to oxygen. These reactions require tremendous temperatures and pressures, conditions found only in the cores of stars at least 8 times more massive than our Sun. Such stars live fast and die young, typically lasting only a few million years before exploding as supernovae and spreading their newly forged elements into space. For oxygen to be distributed throughout a galaxy's interstellar medium requires not just that massive stars have existed, but that they have lived, died, and had their ejecta mixed into the surrounding gas. This is not an instantaneous process. It requires time for supernova remnants to expand and merge with the ambient medium. It requires time for turbulence to homogenize the chemical composition of the gas. The timeline does not work. Or rather, the timeline we thought we understood does not work. Kevin Hainline, a professor at the University of Arizona who helped lead several JD's discoveries, described the emotional experience of these findings. "This is one of the weird, great moments of my scientific career," he said. The discovery of JD's JWST 14-0 reminds him of the dedication of everyone who made Webb possible. Nobody dreamed that there would be galaxies this bright at this high redshift, said George Reiki, another University of Arizona astronomer and former deputy director of Stewart Observatory. The statement captures the genuine surprise that Webb's discoveries have brought. All of these observations together tell us that JD's JWST 14-0 is not like the types of galaxies that have been predicted by theoretical models and computer simulations to exist in the very early universe, said Jake Helton of the University of Arizona. Given the observed brightness of the source, we can forecast how it might grow over cosmic time. And so far, we have not found any suitable analogues from the hundreds of other galaxies we have observed at high redshift in our survey. Brant Robertson of UC Santa Cruz, who helped lead the JD's program, noted the implications for future discoveries. We could have detected this galaxy even if it were 10 times fainter, which means that we could see other examples yet earlier in the universe, probably into the first 200 million years. The records being broken today are unlikely to stand for long. Around the same time, another team discovered something equally strange. Leonardo Ferreira, an astronomer at the University of Victoria in Canada, was analyzing Webb images looking for disk galaxies, the elegant spirals like our own Milky Way. Conventional wisdom held that disk galaxies were relatively rare in the early universe. The constant collisions between small proto-galaxies should have torn apart any delicate spiral structure. Only after billions of years, when the cosmic chaos calmed down, could stable disks form. This expectation was firmly grounded in both theory and observation. In the hierarchical model of galaxy formation, the early universe was a violent place. Small galaxies formed first and repeatedly collided with one another, merging into larger systems. Each merger would disturb the orbits of stars and gas, randomizing their motion, destroying any coherent rotational structure. A disk galaxy requires stars and gas to orbit in a plane, all moving in roughly the same direction. Mergers disrupt this organization. Hubble observations of galaxies at intermediate distances corresponding to the universe when it was a few billion years old showed exactly what theory predicted. Galaxies at this epoch were more irregular, more chaotic, more disturbed than their counterparts in the local universe. The fraction of disk galaxies decreased as you looked back in time. Everything pointed toward disks being a late cosmic development. Ferreira found over 1,600 disk galaxies in the early universe. They were 10 times more common than anyone expected. His team analyzed almost 4,000 galaxies in Webb images, carefully classifying their morphologies. They distinguished between elliptical galaxies, which appear as smooth, featureless blobs, and disk galaxies, which show evidence of flattened rotating structures. The results were striking. Even at the earliest epochs Webb could observe, a substantial fraction of galaxies already showed disk-like morphology. For over 30 years, it was thought that these disk galaxies were rare in the early universe due to the common violent encounters that galaxies undergo, Ferreira said. The fact that Webb finds so many is another sign of the power of this instrument, and that the structures of galaxies form earlier in the universe, much earlier, in fact, than anyone had anticipated. The implications extend beyond cosmology. Disk galaxies represent a relatively stable, organized state of galactic matter. Their orderly rotation allows for long-lived stellar systems and stable chemical enrichment. Our own Milky Way, as a disk galaxy, provides a relatively tranquil environment where planets can form around stars and remain undisturbed for billions of years. This discovery had implications beyond cosmology. Disk galaxies, like the Milky Way, are thought to provide stable environments for the development of complex chemistry, possibly even life. If such galaxies existed much earlier than previously believed, it means the conditions suitable for life may have emerged far sooner in cosmic history than anyone imagined. If disk galaxies were common in the early universe, then potentially habitable environments were also common. Planets could have been forming and evolving around stable stars billions of years before our own solar system coalesced. The window for the emergence of life in the cosmos opens much wider. Ferreira noted the significance. This implies that most stars exist and form within these galaxies, which is changing our complete understanding of how galaxy formation occurs. Based on our results, astronomers must rethink our understanding of the formation of the first galaxies and how galaxy evolution occurred over the past 10 billion years. Not all of Webb's discoveries point toward early organization, however. The telescope has also revealed that many early galaxies were exactly as chaotic and turbulent as theory predicted, just not in the ways we expected. A team led by researchers at the University of Cambridge analyzed more than 250 young galaxies that existed when the universe was between 800 million and 1.5 billion years old. By studying the movement of gas within these galaxies, they discovered that most were turbulent, clumpy systems that had not yet settled into smooth, rotating disks. The researchers used Webb's spectrographs to measure the Doppler shifts of emission lines across different parts of each galaxy. If a galaxy is rotating smoothly, one side will be moving toward us and appear blue-shifted, while the other side moves away and appears red-shifted. The pattern is orderly and predictable. But if a galaxy is turbulent and chaotic, the motions are random and the emission lines are broadened without a clear rotational signature. Most of the early galaxies studied showed signs of intense turbulence. Star formation and gravitational instabilities stirred up so much chaos that the gas could not settle into orderly rotation. These galaxies were messy, irregular, constantly churning. This seems to contradict the disk galaxy findings, but actually it reveals a more nuanced picture. The early universe contained both orderly disk galaxies and chaotic, turbulent systems. The diversity was greater than anyone anticipated. Some regions of the cosmos were calm enough for disks to form and survive. Others were violently stirred by rapid star formation and gravitational interactions. The one-size-fits-all model of early galaxy formation was too simple. Angela Adamo, an astronomer at Stockholm University, who studied the earliest star clusters with Webb, summarized the emerging picture. The early universe is nothing like we expected. Galaxies are more luminous. They form stars at breakneck speed, and they do so in massive and dense star clusters. We are building a new understanding of how early galaxies formed. There is another puzzle from the cosmic dawn that deserves attention, one that reveals just how strange the chemistry of the early universe may have been. Among the most remarkable discoveries was the observation of the earliest galactic merger ever witnessed. A team led by Dr. Kit Boyett of the University of Melbourne used Webb to observe a massive object as it appeared just 510 million years after the Big Bang, roughly 13 billion years ago. What they found was not a single galaxy, but two galaxies in the process of colliding and merging into a larger system. The observations revealed a galaxy consisting of several groups with two components in the main group and a long tail, suggesting an ongoing merger of two galaxies into a larger one, Boyett explained. The merger has not finished yet. We can tell this by the fact we still see two components. The long tail is likely produced by some of the matter being cast aside during the merger. When two things merge, they sort of throw away some of the matter. This was the most distant merger ever observed, and it challenged assumptions about how galaxies grew in the early universe. The hierarchical model of galaxy formation predicts mergers, of course. Small galaxies are supposed to combine into larger ones through repeated collisions. But the scale and maturity of this merger, happening so early in cosmic history, was unexpected. With James Webb, we are seeing more objects in the early cosmos than we expect to see, and those objects are more massive than we thought as well, Boyett noted. Our cosmology is not necessarily wrong, but our understanding of how quickly galaxies formed probably is, because they are more massive than we ever believed possible. The merger observation also provided clues about the chemical evolution of early galaxies. By analyzing the spectral signatures of the merging system, astronomers could detect the presence of heavy elements that must have been produced by previous generations of stars. Even at this early epoch, the galaxies participating in the merger had already undergone significant chemical enrichment. GNZ 11 is one of the most luminous galaxies ever observed at extreme distances. A beacon from just 430 million years after the Big Bang. Before Webb, it was studied by Hubble and ground-based telescopes, tantalizing astronomers with hints of its unusual nature. When Webb's spectrographs finally captured its light in detail, they revealed something unexpected, an abundance of nitrogen far exceeding anything the standard models predicted. Nitrogen is a product of nuclear fusion in stars. Like oxygen, it is not primordial. It must be manufactured through the CNO cycle, a sequence of nuclear reactions that occurs in the cores of stars more massive than about 1.3 solar masses. The CNO cycle converts hydrogen into helium, just like the simpler proton-proton chain that powers our sun. But it uses carbon, nitrogen, and oxygen as catalysts. In the process, it produces more nitrogen. But here is the puzzle. The CNO cycle requires carbon and oxygen to already be present. You cannot run the cycle without the catalysts, and creating carbon and oxygen requires stellar evolution, massive stars living and dying and spreading their fusion products into space. This takes time. Yet GNZ 11, observed at a cosmic age when multiple generations of stellar evolution should barely have been possible, shows nitrogen abundances more than 4 times the solar value. The nitrogen to oxygen ratio in this galaxy is extraordinarily high, far higher than in any comparable system in the local universe. Andrew Bunker of the University of Oxford led one of the teams analyzing Webb's spectroscopy of GNZ 11. Our NIR spectroscopy confirms that GNZ 11 is a remarkable galaxy with extreme properties seen 430 million years after the Big Bang, he wrote. Several explanations have been proposed. One involves Wolf-Rayet stars. extremely massive stars that lose their outer layers through powerful stellar winds, exposing nuclear-processed material from their cores. These stars are prodigious producers of nitrogen through the CNO cycle. If GNZ11 experienced an intense burst of massive star formation, with many Wolf-Rayet stars forming and dying in quick succession, the nitrogen enrichment might be explained. Another possibility involves supermassive stars, hypothetical objects with masses of thousands or even tens of thousands of solar masses. Such stars, if they existed in the early universe, would have extremely short lifetimes and would process enormous amounts of hydrogen through nuclear fusion, potentially producing the observed nitrogen enrichment. Chiaki Kobayashi of the University of Hertfordshire developed a model based on intermittent star formation that can reproduce the nitrogen abundance without requiring exotic stellar populations. In her model, brief but intense bursts of star formation, separated by quiescent periods, can temporarily produce high nitrogen to oxygen ratios. In the brief period in our model, estimated as only 1 million years, the nitrogen abundance is much more enhanced than oxygen, she explained. The nitrogen puzzle in GNZ11 is just one example of the chemical mysteries Webb is uncovering. The early universe was not simply a scaled-down version of today's cosmos. The conditions were different. The stellar populations were different. The chemistry was different. Understanding these differences is essential to understanding how the universe we inhabit came to be. As discoveries accumulated, the scientific community began wrestling with a fundamental question: is cosmology broken? The phrase became a kind of shorthand for the possibility that the Lambda-CDM model, our carefully constructed map of reality, might have a serious flaw. Some researchers wondered whether the observations could be explained by adjustments to existing physics. Others began exploring more radical possibilities. In a paper published in monthly notices of the Royal Astronomical Society, physicist Rajendra Gupta analyzed Webb data and concluded that the structure and masses of very early universe galaxies may be as evolved as the galaxies in existence for 10 billion years. He argued that the findings were in strong tension with the Lambda-CDM model. Mike Boylan-Colchin of the University of Texas at Austin published an influential analysis examining the most extreme early galaxy candidates. If the masses are right, then we are in uncharted territory, he wrote. We will require something very new about galaxy formation or a modification to cosmology. His paper laid out the stark mathematics. The Lambda-CDM model sets firm limits on how much mass can be contained in dark matter halos at any given epoch. These halos provide the gravitational scaffolding for galaxy formation. If a galaxy is more massive than its host halo can provide, something is fundamentally wrong. The extreme early galaxies Webb was finding pushed against these limits and, in some cases, seemed to exceed them. But strong tension is not the same as broken, and this is where the story gets interesting, because the scientific response to Webb's discoveries has been neither panic nor denial. It has been exactly what science is supposed to be: a rigorous, ongoing investigation of what we do and do not understand. One of the first proposed explanations for Webb's impossible galaxies involved measurement errors. When you are looking at objects 13 billion light-years away, appearing as tiny smudges of infrared light, it is easy to make mistakes. Perhaps the redshifts were wrong. Perhaps galaxies were being placed too early in cosmic history when they were actually more recent. Perhaps the mass estimates were inflated by some systematic bias. This is not paranoia. It is scientific due diligence. Every major discovery in astronomy has initially been met with skepticism, and that skepticism has often been justified. History is littered with announcements of groundbreaking results that turned out to be measurement errors, statistical flukes, or misinterpretations of data. Remember the excitement over potential biosignatures in the atmosphere of Venus in 2020. Subsequent analysis showed the detection was likely spurious. Remember the faster-than-light neutrinos announced by the Opera collaboration in 2011? A loose cable was to blame. Remember the detection of primordial gravitational waves by BICEP 2 in 2014. Dust contamination explained the signal. Scientists had every reason to be cautious about Webb's early galaxy findings. The stakes were high. The claims were extraordinary. The bar for evidence had to be correspondingly high. Astronomers attacked this possibility with typical thoroughness. In 2024, a team led by University of Texas at Austin graduate student Catherine Chorowski conducted a detailed analysis of the little red dots as part of the Sears survey. They discovered something important. Many of the objects that had initially been identified as impossibly massive early galaxies were not actually galaxies at all. The team's methodology was rigorous. They obtained spectroscopic observations of their sample, breaking the light from each object into its component wavelengths. Spectroscopy reveals information that imaging alone cannot provide. It shows emission lines from hot gas, absorption features from stars, and signatures of active galactic nuclei. By analyzing these spectra, the team could determine what was actually producing the light they were seeing. The team found that a significant fraction of little red dots showed signatures of active galactic nuclei, supermassive black holes at their centers that were pumping out enormous amounts of light. This extra light from the black holes was making the objects appear more massive than they actually were. The researchers were mistaking black hole radiation for starlight. Stephen Finkelstein, a professor of astronomy at the University of Texas and co-author of the study, explained the implications. So, the bottom line is there is no crisis in terms of the standard model of cosmology. Anytime you have a theory that has stood the test of time for so long, you have to have overwhelming evidence to really throw it out. And that is simply not the case. When scientists removed the black hole contaminated objects from their analysis, the remaining early galaxies were not so massive that they broke physics. They were still somewhat more numerous and larger than predicted, roughly twice as many massive galaxies as expected. But this was a puzzle rather than a crisis. The standard model had survived its first serious challenge from Webb, but the relief was tempered by a deeper question. Even if the standard model was not broken, why had it failed to anticipate what Webb would find? The predictions for the early universe had been clear: small, faint, chaotic galaxies dominating the cosmic landscape. The reality was different: bright, massive, organized structures appearing earlier than anyone expected. Some researchers began exploring whether modifications to the standard model might be necessary, not because the Lambda-CDM framework was fundamentally wrong, but because some of its assumptions about galaxy formation physics might need revision. one line of inquiry involved modified gravity theories. In the standard model, gravity behaves according to Einstein's general relativity, which has been tested with extraordinary precision in the solar system and in observations of gravitational waves. But what if gravity behaves slightly differently on cosmological scales? What if the effective strength of gravity in the early universe was higher than today, allowing structures to form more quickly? Stacy McGaw, an astrophysicist at Case Western Reserve University, has long advocated for alternatives to the standard dark matter paradigm. He noted that modified Newtonian dynamics, or MOND, a theory that modifies gravity rather than invoking dark matter, had actually predicted that large galaxies could appear rapidly in the early universe. What the theory of dark matter predicted is not what we see, McGaw said, pointing to Webb's discoveries as potential support for alternative gravitational theories. Most cosmologists remain skeptical of such alternatives. The Lambda-CDM model has too much supporting evidence, from the cosmic microwave background to the distribution of galaxies to the dynamics of galaxy clusters, to be easily abandoned. But the Webb observations have at least raised the question of whether refinements or extensions might be needed. Another possibility involves early dark energy, a hypothetical component that would have briefly accelerated the universe's expansion shortly after the Big Bang before dissipating. Early dark energy could help reconcile both the Hubble tension and the abundance of early galaxies by effectively giving the universe more time to form structures before the epoch we observe. These alternative theories remain speculative. The scientific community has not embraced them, but their existence demonstrates how Webb's discoveries have opened new avenues of investigation, forcing researchers to consider possibilities they might previously have dismissed. But puzzles demand solutions. And even if Webb's discoveries do not break cosmology, they clearly reveal that something about our understanding of galaxy formation is incomplete. One promising explanation involves a phenomenon called bursty star formation. In the modern universe, galaxies like the Milky Way form stars at a steady, relatively constant rate, about one solar mass per year. Gas slowly cools and collapses. New stars ignite at a rate that balances the depletion of gas with fresh inflows. The process is calm, orderly, continuous, but simulations suggest that in the early universe, star formation may have been far more chaotic. Guoqiao Sun of Northwestern University and his colleagues explored this idea using computer models of early galaxy evolution. Their approach was to simulate the full physics of gas dynamics, stellar evolution, and feedback effects in young galaxies. Tracking how star formation proceeds under the extreme conditions of the cosmic dawn, they found that young galaxies could experience intense, short-lived bursts of star formation, periods where stellar birth rates spiked to 10 or even 100 times normal levels before crashing back down. The physics behind bursty star formation involves a complex interplay of processes. In a young, small galaxy with limited gravitational potential, the feedback from star formation can be catastrophic. When massive stars die as supernovae, they inject enormous amounts of energy into their surroundings. In a small galaxy, this energy can be enough to blow gas completely out of the system, temporarily halting star formation. The galaxy goes dark, but gravity never stops working. Eventually, the expelled gas falls back into the galaxy, cools, collapses, and triggers another burst of star formation. The cycle repeats: burst, blowout, infall, burst, blowout, infall. The galaxy flickers like a failing light bulb, bright, then dark, then bright again. During these bursts, galaxies would briefly shine with extraordinary brightness, making them visible across vast cosmic distances. Between bursts, they would fade to near invisibility. This means that when we observe the early universe with Webb, we are preferentially seeing galaxies during their brightest phases, during their stellar fireworks. The quieter, dimmer galaxies vastly outnumber them but remain hidden. The mathematics of selection effects is important here. If we can only detect galaxies above a certain brightness threshold, and if galaxies spend only 10% of their time above that threshold during bursts, then we are seeing only the tip of an iceberg. For every bright, bursty galaxy Webb detects, there may be 9 more in a quiescent phase, too dim to see. Bursty star formation naturally explains the abundance of bright galaxies at cosmic dawn, Sun wrote. The key is to reproduce a sufficient amount of light in a system within a short amount of time. That can happen either because the system is really massive or because it has the ability to produce a lot of light quickly. Claude-André Faucher-Giguère, an astronomer at Northwestern and Sun's collaborator, added context that helps explain why bursty star formation leads to apparent overestimates of galactic mass. Most of the light in a galaxy comes from the most massive stars. Because more massive stars burn at a higher speed, they are shorter lived. They rapidly use up their fuel in nuclear reactions. So the brightness of a galaxy is more directly related to how many stars it has formed in the last few million years than the mass of the galaxy as a whole. This is a subtle but crucial point. When we estimate the mass of a distant galaxy, we typically do so by measuring its brightness and assuming some relationship between brightness and stellar mass. But this relationship assumes a steady state of star formation. If a galaxy is in the middle of a burst, it will be dominated by young, massive, bright stars. It will appear far more luminous than its total stellar mass would suggest if star formation were continuous. In other words, Webb's impossibly bright early galaxies may not be impossibly massive. They may simply be caught at the peak of a burst, temporarily shining far brighter than their actual stellar content would suggest. The Northwestern team's simulations demonstrated that bursty star formation could not only explain the abundance of bright early galaxies, but also replicate their observed properties with remarkable accuracy. The number of bright galaxies, their colors, their inferred star formation rates all match the Webb observations without requiring any changes to the fundamental parameters of the Lambda-CDM model. If star formation happens in bursts, it will emit flashes of light, Sun explained. That is why we see several very bright galaxies. The bursty star formation model has another important implication. It helps explain the epoch of reionization. This was the period, ending roughly 1 billion years after the Big Bang, when the universe transitioned from neutral to ionized. The first galaxies emitted enough ultraviolet light to strip electrons from the hydrogen atoms permeating intergalactic space, ending the cosmic dark ages and making the universe transparent to light. The puzzle was that the bright galaxies Webb was finding seemed capable of producing far more ionizing radiation than needed to complete reionization. If these galaxies were truly as massive and prolific as they appeared, they should have finished reionizing the universe much earlier than observations suggested. Bursty star formation resolves this tension. During bursts, galaxies are bright and produce lots of ionizing photons. Between bursts, they are dim and contribute little to ionization. The average ionizing output, integrated over the full duty cycle of bursts and quiescence, matches what is needed to explain the observed timeline of ionization. Ryan Ensley of the University of Texas at Austin led an investigation into early galaxies as part of the JADES program. Almost every single galaxy that we are finding shows these unusually strong emission line signatures indicating intense recent star formation, he said. These early galaxies were very good at creating hot, massive stars. The picture that emerges is of an early universe crackling with activity, galaxies flickering on and off like fireflies, their combined light gradually clearing the cosmic fog and ushering in the transparent universe we inhabit today. Another piece of the puzzle involves supermassive black holes and how they manage to grow so large so quickly. In the local universe, supermassive black holes appear to grow through a gradual process of accretion and mergers. Stellar mass black holes form when massive stars die. These merge with other black holes, gradually building up mass. They feed on gas and dust from their surroundings. Over billions of years, they can reach masses of millions or billions of suns. The process is constrained by fundamental physics. When a black hole consumes matter, that matter heats up as it spirals inward, forming an accretion disk. The disk gets so hot that it glows with intense radiation, pushing outward against any infalling material. This radiation pressure sets a fundamental limit on how fast a black hole can grow, known as the Eddington limit. At the Eddington limit, the outward pressure from radiation exactly balances the inward pull of gravity. Any material trying to fall in is pushed away. The black hole can still grow, but only at a maximum rate determined by its mass. For a stellar mass black hole of 10 solar masses, the Eddington limit allows growth to perhaps 1 million solar masses over 1 billion years, assuming continuous feeding. For supermassive scales of billions of solar masses, you need multiple billions of years. But this process takes time. According to standard models, there simply was not enough time in the first billion years for black holes to grow to the supermassive scales that Webb is now observing. The black holes appear too big, too early. The numbers make the problem stark. Consider a black hole that starts at 100 solar masses, perhaps the remnant of a massive population 3 star. Even if it feeds continuously at the Eddington limit for 1 billion years, it can grow to about 100 million solar masses. This is impressive, but falls short of the multi-billion solar mass black holes observed in some early quasars. And 1 billion years is the age of the universe at the furthest redshifts where Webb is finding these objects, meaning the black holes had even less time to grow. Hannah Eubler of the Max Planck Institute for Extraterrestrial Physics was part of a team that studied a particularly extreme example, a naked black hole designated QS01 that existed just 750 million years after the Big Bang. Very simply, at such early epochs in the universe, there was not enough time to produce such monsters starting from small seeds, she said. The QS01 observations were remarkable for what they revealed about the black hole's environment. Unlike typical quasars, which are surrounded by substantial host galaxies, QS01 appeared nearly naked, with very few stars in its vicinity. The black hole dominated its environment almost completely, with a mass tens of millions of times that of the Sun, but a stellar population that was surprisingly meager. Several theories have emerged to explain this black hole problem. One possibility is that black holes in the early universe fed much faster than previously thought, exceeding the so-called Eddington limit that normally caps how quickly a black hole can grow. When a black hole feeds too aggressively, the radiation it produces pushes away its food supply. But if dense clouds of gas could sustain a constant flow despite this outward pressure, black holes might have grown at super Eddington rates. Super Eddington accretion requires special conditions. The gas must be dense enough and the inflow rate high enough that photons become trapped in the infalling material rather than escaping to exert outward pressure. Numerical simulations suggest this is possible in the dense, gas-rich environments of the early universe, where gas had not yet been processed through many generations of stars and remained relatively pristine and abundant. Another possibility is that early black holes simply started bigger. Instead of forming from the collapse of individual massive stars, they may have formed through the direct collapse of enormous gas clouds, giving them a head start of thousands or millions of solar masses right from the beginning. This direct collapse scenario requires the suppression of normal star formation in the collapsing cloud. Usually, as gas cools and condenses, it fragments into smaller clumps that form individual stars. But if the cooling is inhibited, perhaps by intense ultraviolet radiation from nearby galaxies, the cloud can collapse as a single massive object. The result would be a seed black hole, far more massive than any stellar remnant. A more exotic suggestion involves primordial black holes, hypothetical objects that might have formed in the very first moments after the Big Bang, before stars or galaxies existed. Andrea Ferrara of the Scuola Normale Superiore and colleagues have proposed that primordial black holes could have acted as seeds around which the first galaxies formed. If true, some of Webb's little red dots might not be galaxies at all, but black holes that predate the first stars, shining by devouring pristine cosmic gas. Primordial black holes are an old idea, first proposed in the 1970s, but they have gained renewed attention in the era of gravitational wave astronomy, when LIGO and Virgo detected merging black holes. Some of those black holes had masses that did not fit neatly into expectations from stellar evolution. Primordial black holes, formed from density fluctuations in the very early universe, could potentially explain these observations and the early supermassive black holes that Webb is discovering. Theories involving substantial formation of stars prior to or together with the black hole formation and growth are very unlikely, Hubble noted. The observations seem to demand that the black holes came first, or at least formed alongside the first stars, rather than waiting for multiple generations of stellar evolution. In September 2025, an international team, including researchers from Penn State, made headlines with an even stranger proposal. They suggested that some of the little red dots might be an entirely new type of astronomical object, a black hole star. A black hole star, or BH*, as the researchers called it, would consist of a supermassive black hole at the center, surrounded by an enormously thick shell of hot gas. The black hole would feed on this gas, converting matter into energy and light. But instead of the classic quasar structure with an exposed accretion disk and powerful jets, the entire system would be wrapped in a dense hydrogen atmosphere. The concept draws on decades of theoretical work about the possible configurations of matter around black holes. In a normal quasar, we see the accretion disk directly. Light from the super-hot inner regions escapes relatively freely, giving us the characteristic broad emission lines and high-energy radiation that define these objects. But what if the accretion rate was so extreme that light could not easily escape? What if the material falling toward the black hole formed not just a thin disk, but an enormous, puffy envelope that trapped much of the radiation? From the outside, a black hole star would look almost like a normal star, with spectral features resembling stellar atmospheres. But the energy source would be completely different: gravitational accretion rather than nuclear fusion. The key distinction is the source of the luminosity. A normal star shines because nuclear fusion reactions in its core release energy. 4 hydrogen nuclei fuse into one helium nucleus, releasing a tiny amount of mass as energy according to Einstein's equation, E equals mc squared. This process can sustain a star for millions or billions of years, depending on its mass. A black hole star would shine through gravitational accretion. As matter falls toward the black hole, it converts gravitational potential energy into radiation. This process is actually more efficient than nuclear fusion. Accretion can release up to 10% of the rest mass energy of infalling matter, compared to less than 1% for hydrogen fusion. A black hole star could potentially outshine a normal star of similar mass. The team's analysis was sparked by an object they called the cliff, one of the most extreme little red dots discovered. Its spectrum showed a dramatic feature: a steep rise at ultraviolet wavelengths that defied conventional explanation. Anna de Graaf of the Max Planck Institute for Astronomy in Heidelberg led the analysis. The extreme properties of the cliff forced us to go back to the drawing board and come up with entirely new models, she said. The cliff earned its name from this spectral feature. What astronomers call the Balmer break is normally seen in stellar spectra, a characteristic step in brightness at a specific wavelength caused by the absorption of light by hydrogen atoms in a stellar atmosphere. The cliff showed an extreme version of this feature, more pronounced than in any normal stellar population. The RUBIES program, short for Red Unknown's Bright Infrared Extragalactic Survey, had accumulated nearly 60 hours of Webb spectroscopic observations by the end of 2024, targeting thousands of distant galaxies. When the team examined their sample of little red dots, they found 35 such objects, but the cliff stood out as the most extreme. Our analysis indicates that the tiny pinpoints of light may be giant spheres of hot gas that are so dense they look like the atmospheres of typical nuclear fusion-powered stars. The researchers wrote, however, instead of fusion, they are powered by supermassive black holes in their center that rapidly pull in matter, converting it into energy and giving off light. Joel Leger, who had been part of the team that first identified the universe breakers 3 years earlier, summarized the implications. No one has ever really known why or where these gigantic black holes at the center of galaxies come from. These black hole stars might be the first phase of formation for the black holes that we see in galaxies today. Supermassive black holes in their little infancy stage. If black hole stars are real, they could solve multiple mysteries at once. They would explain why some early objects appeared too bright to be normal galaxies. They would provide a mechanism for rapid black hole growth. And they would offer a glimpse of a phase of cosmic evolution we never knew existed. The black hole star model also has the potential to explain the strange relationship between black hole mass and stellar mass in the early universe. If early galaxies were dominated by black hole stars rather than normal stellar populations, the mass we attribute to stars might actually be mass in these exotic configurations. The apparent oversized black holes might simply reflect a different mode of matter organization, one that we have never observed in the local universe because it is a transient phase that galaxies grow out of. This is the best idea we have, and really the first one that fits nearly all of the data, Leja said. So now, we need to flesh it out more. It is okay to be wrong. The universe is much weirder than we can imagine, and all we can do is follow its clues. There are still big surprises out there for us, but the story does not end there. In January 2026, just as this script was being prepared, astronomers announced yet another category of unexplained objects. A team analyzing Webb data discovered 9 point-like sources that could not be classified as anything known. They were not quasars, which have characteristic broad emission lines. They were not compact galaxies, which should appear at least slightly extended at Webb's resolution. They were not stars, which would show different spectral features and would not be visible at such extreme distances. The discovery emerged from systematic searches through Webb's archival data. The team was not looking for weird objects specifically. They were conducting routine surveys of the early universe, cataloging galaxies and measuring their properties. But these 9 objects refused to fit into any existing category. The researchers nicknamed them Astronomy's platypus because, like the biological platypus that combines features of mammals, birds, and reptiles, these objects combine features that normally do not appear together. When European naturalists first encountered the platypus in the 18th century, they assumed it was a hoax, a fake animal stitched together from parts of different creatures. The astronomical platypuses evoke a similar sense of disbelief. Hao Jingyan of the University of Missouri presented the findings at an astronomical conference. We report a new population of objects discovered using the data from the James Webb Space Telescope, he said. From the low-resolution spectra we have, we cannot rule out the possibility that these 9 objects are star-forming galaxies. However, their very small and compact appearance makes this explanation difficult to confirm. The spectra of these objects showed narrow emission lines, similar to the little red dots, but with different characteristics. The objects were unresolved, appearing as single points of light. They were distant based on their redshifts, but they did not match the properties of any known class of distant object. One possibility is that these platypus objects represent an even earlier stage of galaxy formation than astronomers have ever observed, a phase before recognizable galactic structures have coalesced. If so, they might provide our first direct window into the very moment when darkness ended and light began. Another possibility raised by the team, but requiring further investigation, is that these objects are entirely new phenomena, something not predicted by any existing theoretical framework. The history of astronomy is punctuated by such discoveries, objects that initially seem impossible, but eventually reveal new aspects of how the universe works. Astronomers have one suggestion to explain these odd galaxies, noted a summary of the findings. They think that what Webb has observed is an earlier stage of galaxy formation than astronomers have ever been able to see. If that is the case, then this discovery could lead astronomers to seek answers for much deeper questions like, how does the process of galaxy formation begin? But astronomers would have to find more such objects to study further. The platypus objects remain mysterious. Webb continues to observe them. Follow-up observations with spectrographs may reveal their true nature, or they may deepen the puzzle. This is how science works at the frontier. You find something strange. You investigate. Sometimes the strangeness resolves into something familiar. Sometimes it opens doorways to entirely new understanding. What does all this mean? The honest answer is that we do not fully know yet. Science is not a process that delivers final answers on demand. It is an ongoing conversation between theory and observation, hypothesis and evidence, models and measurements. But we can begin to sketch the outlines of what Webb has revealed about the early universe, even if many details remain unclear. First, the early universe was more efficient at forming stars than we expected. Whether through bursty star formation, different initial mass functions, or some other mechanism, the first galaxies converted gas into stars at rates that pushed the limits of what our models predict. The cosmic dawn was not a gentle awakening, but a violent conflagration, with star formation proceeding at breakneck speed. Second, supermassive black holes may have formed earlier and by different mechanisms than we thought. The existence of overmassive black holes in young, small galaxies suggests that the standard pathway of gradual accretion and merger is incomplete. Something else was happening. Something that allowed black holes to reach enormous masses within the first billion years. Whether this involves direct collapse, primordial black holes, super Eddington accretion, or entirely new physics remains to be determined. Third, the chemical enrichment of the universe proceeded faster than expected. The detection of oxygen, nitrogen, and other heavy elements in the most distant galaxies shows that stellar nucleosynthesis was already in full swing when the universe was only a few 100 million years old. Multiple generations of massive stars had already lived and died, spreading their fusion products throughout the interstellar medium. Fourth, stable galactic structures formed earlier than we anticipated. The abundance of disk galaxies in the early universe shows that the chaotic merging process we imagined was not the whole story. Somehow, orderly rotation and coherent structure could emerge even in the violent conditions of the cosmic dawn. Fifth, there may be entirely new types of astronomical objects waiting to be understood. Black hole stars, platypus objects, and the most extreme little red dots may represent phases of cosmic evolution we never knew existed. The taxonomy of the universe may need to be expanded. What we can say is this: the James Webb Space Telescope has revealed that the early universe was far more complex, far more active, and far more mysterious than we expected. Galaxies formed faster, Stars burned brighter, black holes grew larger. The cosmic dawn was not a gentle awakening, but a violent, prolific explosion of structure and energy. The Lambda-CDM model is not broken, but it is incomplete. The standard model of cosmology correctly describes the broad strokes of cosmic evolution. From the Big Bang, through the formation of the cosmic microwave background, through the large-scale structure of the universe we observe today. What Webb has shown us is that the details, particularly the details of how the first galaxies and black holes formed, require refinement. This is not a crisis. This is science working exactly as it should. There is another tension worth mentioning, one that predates Webb but has been deepened by its observations. It is called the Hubble tension, and it involves the most fundamental measurement in cosmology, the rate at which the universe is expanding. The expansion of the universe is one of the most profound discoveries in the history of science. In 1929, Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they recede. This relationship, now known as Hubble's law, led to the realization that the universe is not static, but expanding. Run the movie backward, and all of space was once compressed into a single point. The Big Bang theory was born. The rate of this expansion is quantified by a number called the Hubble constant, typically measured in units of kilometers per second per megaparsec. If the Hubble constant is 70, that means a galaxy 1 megaparsec away is receding from us at 70 kilometers per second. A galaxy 2 megaparsecs away is receding at 140 kilometers per second, and so on. Knowing the precise value of the Hubble constant is crucial because it tells us the age, size, and ultimate fate of the universe. A higher Hubble constant means a faster expansion, which in turn means a younger universe. A lower constant means a slower expansion and an older cosmos. The difference between 67 and 73 kilometers per second per megaparsec may seem small, but it corresponds to a difference of about 1 billion years in the age of the universe. The expansion rate, called the Hubble constant, can be measured 2 different ways. One approach uses observations of the cosmic microwave background, the ancient light from recombination, and applies the Lambda-CDM model to calculate what the expansion rate should be today. This method yields a value of about 67 kilometers per second per megaparsec. The cosmic microwave background approach works by measuring the tiny temperature fluctuations in the primordial light, then using the physics of the standard model to extrapolate forward in time. If we know the initial conditions of the universe with sufficient precision, and if we know the laws of physics that govern cosmic evolution, we can calculate what the expansion rate should be at any later time. The Planck satellite, which mapped the cosmic microwave background with unprecedented accuracy, gave us extraordinarily precise initial conditions. Together with the Lambda-CDM model, these observations predict a Hubble constant of 67.4 kilometers per second per megaparsec. The other approach measures the expansion directly by observing nearby objects of known brightness, particularly a type of exploding star called a type I supernova, and seeing how fast they are receding from us. This method consistently yields a higher value, around 73 kilometers per second per megaparsec. This direct measurement approach requires what astronomers call a distance ladder. You start with nearby objects whose distances you can measure geometrically. You use these nearby objects to calibrate the brightness of standard candles, objects of known intrinsic luminosity. Then you observe those standard candles at greater and greater distances, using their apparent brightness to determine how far away they are. The most important rungs on this ladder are Cepheid variable stars and Type I supernovae. Cepheids are pulsating stars whose period of brightening and dimming is directly related to their intrinsic luminosity. By measuring the period, you know the intrinsic brightness, and by comparing to the apparent brightness, you get the distance. Type I supernovae are even brighter, visible across billions of light years, and they all have approximately the same intrinsic luminosity, making them excellent distance indicators. The difference, about 9%, may not sound large, but the measurements have become so precise that the gap is now statistically significant to more than 5 sigma, meaning there is less than a 1 in 3.5 million chance that it is a random fluctuation. Some researchers hoped that Webb would resolve this tension by providing more accurate measurements of stellar distances. The issue was that Hubble sometimes struggled to distinguish individual Cepheid stars in crowded, dusty regions of distant galaxies. Perhaps this confusion was biasing the measurements. Webb, with its superior infrared vision, could see through the dust and resolve individual stars more clearly. Instead, observations by Adam Rees and colleagues at Johns Hopkins University confirmed that the discrepancy is real. Webb's data ruled out the possibility that errors in measuring distant stars were responsible for the mismatch. The Cepheids that Webb observed had the same properties that Hubble had measured. There was no systematic error. The distance ladder was accurate. With measurement errors negated, what remains is the real and exciting possibility that we have misunderstood the universe, Rees wrote. The Hubble tension and Webb's early galaxy discoveries may be related. Both suggest that something about the early universe, something about the transition from cosmic dawn to the cosmos we observe today, is not captured by our current models. Perhaps there was an episode of early dark energy that briefly accelerated the universe's expansion. Perhaps dark matter behaves differently than we thought. Perhaps there are forces or particles we have not yet discovered. Mark Kamienkowski, a cosmologist at Johns Hopkins who has helped develop possible explanations for the tension, summarized the stakes. One possible explanation for the Hubble tension would be if there was something missing in our understanding of the early universe, such as a new component of matter, early dark energy that gave the universe an unexpected kick after the Big Bang. The next few years of observations may provide answers, or they may reveal even deeper mysteries. In the midst of all this uncertainty, there is one conclusion that seems increasingly secure. Life may have had a head start. The discovery that disk galaxies, stable spiral structures, like the Milky Way, existed far earlier than expected suggests that habitable environments may have been common when the universe was only a few billion years old. The detection of oxygen and other heavy elements in galaxies that formed within the first few 100 million years means the raw materials for rocky planets and complex chemistry were present from the very beginning. This is worth pausing to appreciate. The building blocks of life as we know it, carbon, nitrogen, oxygen, phosphorus, sulfur, all of these elements were forged in stars. Without stellar nucleosynthesis, the universe would contain only hydrogen, helium, and traces of lithium. There could be no planets, no organic molecules, no life. The discovery that these elements were present so early in cosmic history means that the chemical prerequisites for life were established almost as soon as stars began to form. The first generation of massive stars, living their brief, brilliant lives and dying in supernova explosions, seeded the cosmos with the atoms that would eventually become us. And if disk galaxies were common, then stable environments for planet formation were also common. A planet needs more than just heavy elements. It needs a star that burns steadily for billions of years. It needs an orbit that remains stable, not constantly disturbed by passing stars or galactic mergers. It needs protection from sterilizing radiation. Disk galaxies, with their orderly rotation and well-defined stellar populations, provide these conditions far better than the chaotic, merging systems that were supposed to dominate the early universe. We do not know when or where life first emerged in the universe. We may never know. But Webb has shown us that the cosmic conditions necessary for life, stable galaxies, heavy elements, a universe filled with light, were established far earlier than we imagined. If life arose on Earth 4 billion years ago, it might have arisen elsewhere 10 billion years ago. The implications of that possibility are staggering. Think about what 10 billion years of evolution might produce. Life on Earth went from single-celled organisms to complex multicellular life in roughly 2 billion years, from fish to mammals in another few 100 million years, from early primates to humans with spacecraft and telescopes in just a few million years. If intelligent life arose somewhere else 10 billion years ago, what might it have become in all that time? We have no evidence that such life exists. The famous Fermi paradox asks, if intelligent life is common, where is everybody? Why have we not detected signals, artifacts, or visitors from older civilizations? Webb cannot answer this question directly, but it has shown us that the raw materials for life were available much earlier than we thought, which only deepens the mystery of our apparent cosmic loneliness. Where do we go from here? Webb is still operating, still gathering data, still pushing the boundaries of what we can see. Its instruments are designed to function for at least 10 years, possibly 20 or more, if nothing breaks. Every day, it collects new observations of the early universe, adding pieces to a puzzle we are only beginning to assemble. The telescope's fuel supply, used for orbital maintenance and attitude control, was a major limiting factor in the mission design. The original requirement was for a 5-year mission with a 10-year goal, but the launch on Christmas Day 2021 was so precise, the Ariane 5 rocket placing Webb on such an accurate trajectory that the telescope used far less fuel than expected for its journey to the second Lagrange point. Current estimates suggest the fuel supply will last at least 20 years, potentially longer. Future telescopes will extend Webb's reach. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will survey wider fields, finding statistical samples of early galaxies that Webb can only glimpse individually. Roman's wide-field infrared camera will cover an area of sky 100 times larger than Webb's instruments in a single exposure, enabling surveys of millions of galaxies across cosmic time. Ground-based observatories like the Extremely Large Telescope and the Giant Magellan Telescope will provide complementary data in the optical spectrum. These next-generation facilities, with mirrors 30 meters or more in diameter, will achieve resolutions that exceed even Webb's capabilities in certain wavelength ranges. They will be able to measure the spectra of individual stars in galaxies billions of light-years away, probing the chemical evolution of the cosmos in unprecedented detail. Radio telescopes, like the Square Kilometre Array, will probe the neutral hydrogen that permeated the universe before ionization, potentially letting us hear the darkness before the first stars. By detecting the faint emission from hydrogen atoms in the cosmic dark ages, these instruments may reveal the conditions that preceded the formation of the first galaxies. We may finally be able to study the universe before light, and theorists are already at work, building new models that might explain what Webb has shown us. Simulations like Cosmic Dawn 3 are recreating the early universe with unprecedented detail, searching for the physics that could produce the galaxies, black holes, and mysterious objects that the telescope has revealed. These simulations run on the most powerful supercomputers in the world, tracking trillions of particles as they interact, collapse, and form the first cosmic structures. The interplay between observation and theory is the heartbeat of science. Webb shows us something unexpected. Theorists scramble to explain it. New predictions emerge. Observations test those predictions. The cycle continues, each iteration bringing us closer to truth. Already, Webb's discoveries have inspired a new generation of theoretical work. Dozens of papers have been published attempting to explain the abundance of bright early galaxies. New simulations are being run, pushing supercomputers to their limits. Old assumptions are being questioned. New ideas are being tested. Fabio Pacucci of the Center for Astrophysics at Harvard and Smithsonian, who has studied the little red dots extensively, captured the excitement. Little red dots are arguably the most surprising discovery by JWST to date. They might help us understand how the first black holes formed and co-evolved with galaxies in the early universe. The field is alive with possibility. Every week brings new papers, new observations, new debates. The cosmic dawn, once shrouded in darkness and mystery, is gradually coming into focus. We do not yet have all the answers. We may never have all the answers. But we are asking better questions than ever before. This is what it looks like when science advances. Not a smooth march from ignorance to understanding, but a lurching, iterative process of discovery and confusion, hypothesis and refutation, surprise and explanation. Webb has shown us that the universe is stranger than we knew. Now comes the work of understanding why. The coming years will be decisive. As more data accumulates, patterns will emerge. Some theories will be confirmed. Others will be ruled out. The fog of uncertainty will gradually lift, revealing the true nature of the cosmic dawn. But even when answers come, new questions will follow. That is the nature of exploration. Every summit reveals a new horizon. Every discovery opens new mysteries. The universe is not a puzzle to be solved and set aside. It is an endless frontier, inviting us to keep looking, keep wondering, keep asking why. There is a quote often attributed to the physicist Werner Heisenberg. Not only is the universe stranger than we think, it is stranger than we can think. James Webb has proven this true once again. We built the most powerful telescope in human history, sent it 1 million miles into space, aimed it at the beginning of time, and discovered that our map of reality was missing mountains and rivers and cities we never imagined. The universe told us that we were wrong, not about the broad outlines of cosmic history, but about the details of how galaxies and black holes first came to be. Consider what this means. For decades, physicists and astronomers refined the Lambda-CDM model, testing it against every observation, tweaking its parameters, convincing themselves that they understood how the universe works. And they were right, mostly. The model correctly predicted the cosmic microwave background with exquisite precision. It explained the distribution of galaxies on the largest scales. It accounted for the accelerating expansion of space. But when we finally built an instrument capable of looking all the way back to the cosmic dawn, we found surprises. Not small surprises, not minor adjustments to existing knowledge, but fundamental puzzles that required genuinely new thinking. The early universe was brighter, more massive, more organized, and more productive than anyone anticipated. Some people find this unsettling. If our best model is incomplete, what else might we be wrong about? How can we trust anything science tells us? But this reaction misses the point. Science is not a collection of eternal truths carved in stone. It is a method, a process of systematic observation and hypothesis testing that gradually brings our understanding closer to reality. The Lambda-CDM model has been spectacularly successful precisely because it is willing to be challenged, refined, and improved. The goal of science is not certainty. The goal is to be less wrong tomorrow than we were today. Every discovery that challenges our understanding, every observation that does not fit our models, is not a failure. It is an opportunity. It is the universe inviting us to learn something new. Webb's discoveries do not undermine our confidence in science. They are science in its highest form. The universe is 13.8 billion years old. Life on Earth has existed for roughly 4 billion years. Human civilization spans perhaps 10,000 years. Modern astronomy is barely 4 centuries old. We are infants trying to comprehend infinity. And yet, here we are. We have built machines that can see across billions of light years and billions of years. We have constructed mathematical frameworks that predict the behavior of galaxies, stars, and atoms with extraordinary precision. We have asked the deepest questions that any species can ask. Where did we come from? How did the cosmos begin? Are we alone? Webb cannot answer all these questions. No telescope can. But it has shown us something profound. The universe is vaster, stranger, and more beautiful than we knew. And there is so much more to discover. Consider what we have accomplished in just a few years of Webb operations. We have found the oldest galaxies ever observed, pushing our vision back to within 300 million years of the Big Bang. We have discovered entirely new classes of objects, little red dots and black hole stars and platypus galaxies that defy classification. We have detected oxygen at the edge of observable space. We have confirmed that the Hubble tension is real. We have shown that disk galaxies and heavy elements existed far earlier than expected. And we are just getting started. The deepest observations are still ahead of us. The most sensitive surveys have not yet been conducted. The statistical samples that will allow us to distinguish between competing theories are still being accumulated. Webb has opened a window on the cosmic dawn, but we have only begun to peer through it. We stand at the edge of cosmic dawn, peering into the first light, watching as reality reveals secrets that have been hidden for 13 billion years. The map we trusted has been redrawn. The story we told ourselves has gained new chapters, and the questions that remain about black holes and galaxies and the physics of the early universe are more tantalizing than ever. This is not the end of the investigation. This is the beginning. The telescope keeps watching, the data keeps flowing. And somewhere out there, in the light of galaxies that formed before our sun was born, the answers are waiting. If you have made it this far, you have just traveled 13.8 billion years and back. You have witnessed the Big Bang, the Dark Ages, the cosmic dawn, and the birth of impossible galaxies. You have encountered black hole stars and little red dots and platypus objects that defy classification. You have seen science confronted with its own limitations and watched it do what it always does: ask more questions, gather more data, build better models. This is the power of curiosity. This is the reward of looking up. The universe does not care whether we understand it. The galaxies shine regardless of whether anyone is watching. The black holes feed whether or not we know they exist. But we do watch. We do try to understand. And in that trying, in that relentless human desire to know, we become something more than the particles and energy that compose us. We become witnesses to the cosmos, the universe looking back at itself, wondering at its own existence. James Webb has shown us that there are still secrets in the sky. Mountains on maps marked flat, rivers flowing in directions no one expected, cities thriving in ages thought empty. And that, perhaps, is the most hopeful discovery of all. No matter how much we learn, no matter how far we see, there is always more to know. The mystery never ends. We simply get better at asking questions.